Encodings take something and convert it into a different form. How computers handle text used to confuse me. I've realized that much of that confusion stemmed from not having a firm grasp on other related concepts. For example, the data type char in C suggests that it stores a character, yet this is not valid. A much better name would be a byte, like it is in other languages. There are historical reasons for this, which we will get into. But in the case of text encodings, there are many small concepts like this. They have relations to each other, and together create the bigger picture. An incomplete understanding of even one aspect can seriously impact how one perceives the others. The most fundamental one is probably binary. So let's start there and brush up our memory on number systems. Decimal, or base 10, is what we humans use, and it simply means that each position, going from the right, is 10 times more valuable than the one before. They are then multiplied by the corresponding digit. After summing it all up, we get the number. Of course, binary works in the same way, but because doubling is slower than 10xing, we're going to need more digits to write that same number. Hexadecimal can be found in many places, and it's important to know it's also a number system, not an encoding. To cover all 16 values, A to F is added. So because a single digit can be any of the 16 values, it does the job of 4 bits in binary, also known as a nibble. Add one more and you get a byte. This is why, for example, hex pairs are often used when debugging raw memory bytes, as dealing with pure binary wouldn't be very pleasant. So because computers only operate on bits and numbers, the only way we can ever interact with them in our language is if we can map numbers to letters. And ideally, we should agree on the same mappings, since that would allow us to connect our computers together, a prerequisite for the internet. One of the oldest and most widely used character set is ASCII. It uses 7 bits for 127 slots. The first 32 are special control characters. For example, 13, the carriage return, instructed a typewriter to move its printhead to the beginning of the line. We also have things like line feed and tabs. But most of these control characters are obsolete, designed for old protocols. Which brings us to the printable characters, symbols, digits, and the English letters. To build further intuition, uppercase letters start with the leftmost bit on. 32 later, the lowercase letter starts. Unfortunately, ASCII is missing all of the other letters used by the world. Some countries tried to extend it using the last bit, and others created completely new character sets. Eventually though, the world settled on the amazing Unicode standard, which can hold over 1 million characters. As of making this video, only around 150,000 have been used. We have the letters from the languages and scripts, mathematical symbols and other special characters, and even emojis. Every character is assigned a number. But in Unicode, they are referred to as code points, which is just a number in hex, along with a special prefix. An important property of Unicode is that all of the ASCII characters are assigned the same number. We'll see why that's important later. But how do we actually use this? The simplest approach would be to use just enough bits to cover all of the Unicode characters, which is 21, and probably add 3 more to make 3 full bytes instead. We can then encode each character using its code point, but in binary, and fill the unused bits with zeros. And decoding data would also be super simple. Just scan 3 bytes at a time. However, there are 2 big issues. One, it breaks ASCII compatibility. Programs that expect ASCII assume every byte is a character. But maybe the bigger issue is what we saw earlier during the encoding. These zeros are very wasteful. regular ASCII files would take up 3 times as much space as before. This is a fixed length encoding, and while this 3-byte encoding never caught on, UTF-32, which uses 4 bytes and thus 32 bits, is exactly like this. We needed something better. Depending on the character, UTF-8 uses between 1 and 4 bytes, and it achieves this by having 2 types of bytes. A continuation byte that will always start with a 1 and a 0, and starting bytes, which can be in 4 different states. It can start with a 0 for a single byte character, or it can start with a sequence of 2 to 4 ones, followed by a 0, to indicate a character of that many bytes. In the case of a single byte character, the remaining 7 bits are used to construct it. No continuation bytes are needed. This means that all ASCII text is also valid UTF-8. When encountering a multi-byte character, it is clear from the starting byte how many are needed. In this case, there are 3 ones, so it's a 3-byte character. 1 starting and 2 continuation, making just enough room for the code points. This makes decoding a stream of bytes pretty straightforward. If it starts with a 0, we know it's a single byte character. If it starts with 1s, we know how many continuation bytes we can expect. And if something goes wrong, like data corruption or missing bytes, we can easily recover by going to the next starting byte. UTF-8 is nothing short of incredible, but without talking about the not-so-great UTF-16, this video wouldn't feel complete. Because initially, Unicode had a much smaller capacity, around 65,000, or 2 to the 16. And because UTF-8 wasn't yet widely adopted, there was UCS2, a fixed-length 2-byte per character encoding. When Unicode later expanded to its current capacity, UTF-16 was invented to encode those new code points using 4 bytes, remaining compatible with UCS2 by being a variable length encoding. I won't cover exactly how it works because it is used so rarely today. Just know that it encodes each character using either 2 or 4 bytes. Another essential encoding is base64, which initially had me confused. Many online examples demonstrate how it works by converting plain text into base64, which obscures the main purpose, which is to convert any binary data into readable text. Take for example an image in the JPEG file format. Its data describes the image, like the color of pixels and so on. If we try and view it using a text editor, it will look very weird. That's because the terminal is trying to decode it with UTF-8. Now, consider embedding an image within HTML. We can do so by using the source attribute. This text, at its core, is just bytes. So, if we were to insert the image data directly as it is, it would be the equivalent of inserting what we saw earlier, which would make the HTML unreadable. By base64ing the image first, we get text that won't break the HTML. The way it works is by defining a table of 64 characters. During encoding, the data is split into chunks of 6. These chunks then index the table and produce the base64 text. It's common to see base64 strings end with equal signs. This occurs when the total number of bits in the input isn't evenly divisible by 6. While there are many more encodings and nuances I could cover, I hope this video can serve as a good foundation for understanding the most crucial concepts. Thank you so much for watching.